Questions?
Yeah. Yeah, when you proved that the alpha span dual space, you said that if they don't span, there must be some edge cut down in such that it gets mapped to zero under all the rules. Right?
Yeah, I mean, let me see, where is that proof? Which page was it?
12.4.
Huh?
Theorem 12.4. 12.4.
12.4. Theorem 12.4. Huh? Yeah. So what was the statement again? Sorry, in 12.4, theorem 12.4.
12.3 because yeah, 12.3 has 6 points, right?
12.3, 12.3.
So it's 6 1.
Sixth one. Right, so, yeah, correct. Yeah. So the statement was, so the point was the statement is alpha belonging to delta span H star, right? That is the H star. Okay. If the roots alpha do not span, they must exist on A H point. So that, right. Yeah. So yeah, exactly. What is the question? Your doubt is what? The existence of such a H?
Yeah. How can you say that?
Yeah. I mean, if they do not span, I mean, so what does it mean to span, right? So, I mean, H itself is in the H, right? This is the original Kartha algebra, right? So now these are so we are talking about, these are the space of linear functions, right? So if it doesn't span all of them, I mean, okay, one way to, how to say this? You know, I don't know, maybe this is probably not completely clear. Why this is, why the space of linear functions, it has the same dimensionality as the dimension of this, right? Is that clear to all of you? I mean, the easiest way to think about is that, okay, let's suppose this is some n-dimensional space, right? This H is n-dimensional space. Choose some basis, H1 up to Hn, right? It's a vector space, so you can choose a basis. Then any H can be written as some combination AI, Hi, right? Where AI are some numbers, real or complex, depending on whatever your space is. Okay. Now what we want is we want to write down some function, let's say alpha of H, linear function, right? So linear function, this would mean that this will be something like some combinations alpha 1, alpha I, Hi, right? Because H itself is a linear combination. So alpha, let's call it alpha Hi. Alpha I, Hj is delta Ij. So this is my basis. This is my basis for the linear functions. So what I'm claiming is that if I choose a function like this, if I define a function which is like of this type, right? I mean, it's enough to specify how the function acts on the basis, right? Because once I know for the basis, then clearly alpha I acting on H, where H is of this form, is going to be AI, say J, alpha I, Hj, right? Summed over J, correct? Because it's linear. Function is linear. Is that clear? But now I can choose this basis delta Ij, so that just makes it this is equal to AI. So any function now, I mean, any function I can write, any function alpha, I can write it as some coefficients, I don't know, let's say bi alpha I, some delta. So this is the space of linear function. Now suppose that alpha doesn't span. Okay, alpha doesn't. These roots now do not span. So this, sorry, I shouldn't have used the same notation. Just call it beta. So beta is here. Now let's suppose that the set of all the roots that we have do not span this entire thing. So that means, so for example, so let's say, just to take a simple example, these alphas do not span all of the things. So let's say some beta n is missing, let's say. Fine. Something is missing. Some element is missing here, right? So let me just take as a simple example, say beta n is missing here. Say this spans only n minus 1 dimensional space. Okay. The H is n dimensional, this is H n dimensional, and H star should also be n dimensional, right? But what we are saying is that the roots that you have in your problem, in your particular Lie algebra, whatever it is, it doesn't span all of that space. Okay? It spans less. Let's say, let's take an example, n minus 1 dimensional space. Okay? Then, and call that thing as beta n, which is missing. Okay? That's just an example. It doesn't have to be. It can be some linear combinations of these betas, which is missing. Okay? So, just to get a intuitive picture, if beta n is missing, that means all the alpha acting on H, this basis, Hn, will be equal to 0, correct? Because what we are saying is that alpha, any alpha, can be expressed as linear combinations of beta I, but I going from 1 to n minus 1, right? Bi, correct? Because we are saying that beta n is not spanned by these alphas. Right? Okay. So any alpha, I can write it in this form. Any alpha, which is the root, of course, right? So any alpha belonging to delta, I can express it in some combinations like this. Okay. So now if I take this alpha and let it act on Hn. Okay, Hn is this basis. Then this is the same as sum over Bi, beta I on Hn. And this is I going from 1 to n minus 1. But this is delta In. Right? So this will be identically 0. So this is, of course, I took some simple example, beta n is missing, but if this is not spanning all the full space, then there will be some linear function which you can never get starting from here, right? Okay. And then there will be some element inside in the H space where all of these functions give you 0. All of the functions contained in delta. So that was the argument here. Any other question?
In theorem 12.5.
12 point?
Yeah.
12.1.
1.5.
12.5. Yes, which statement is that?
Third statement.
The first statement, right? Third statement.
Yeah. If we put beta equal to minus alpha, does the proof or does it hold? If we do beta equal to minus alpha as a particular root, does this statement hold?
There is a set of roots. Yeah. So this was the statement. This was the point that we wanted to prove that this quantity is not 0, right? Because in general we said that if I have x alpha, x beta, then whatever it is, it's going to be something which has a root alpha plus beta. The roots are additive. So it's going to be proportional to x alpha plus beta times some coefficient. Right? Now, so the idea of this statement is that this coefficient is necessarily non-zero. Right? That is the point. So
even for beta equals to minus 1.
Is it delta equal to?
Beta equals to minus alpha. Okay.
No, this I am taking alpha plus beta not equal to 0, right? I mean, for beta equal to minus alpha, we already have this will be in kata, no? This will be in the kata.
So it can be 0.
No.
Proportional to the kata killing form.
Kata killing form, yeah. Yeah. No, that cannot be 0. X alpha is x minus alpha. I mean, it was not one of the statements. I have even forgotten what. There's so many theorems we have gone through. Yeah. I mean, so I mean, you are asking whether bx alpha x minus alpha is not 0, right? That is what you're asking. Because anyway, the statement is that this is going to be, that is one of the statements we proved, right? That x alpha x minus alpha is equal to b x alpha x minus alpha h alpha. Right? No, that was the statement. I mean, that comes from the non-degeneracy of the Cartan killing form, right? Because if you take, so again, we were saying that let's choose a basis for the Lie algebra as the first guys in the Cartan. So let's say these are the H. Right? So this is the R-dimensional. This is the R-dimensional subspace, which is just the Cartan subalgebra. So choose some basis for the Cartan subalgebra and put them here. So let's say H1 up to HR. There are independent. Then you start putting all the non-zero roots, x alpha, x beta, etc. So in this basis, you see that because add x alpha takes some x gamma to x alpha plus gamma. Okay. Then this will be purely off diagonal, right? Let me see. So the structure would be, if I look at the add action, it was, I can again think in terms of the blocks. So H with H is 0, that is fine. H with the x alphas are going to give me some alphas here. Right? Okay. X alpha with x beta is going to be, this is what I'm trying to say is purely off diagonal. Okay. So the only way the B, the Cartan killing form, can be non-zero is if there exists now x minus alpha. Okay. It's clear. If I take bx alpha with x beta, this is going to be 0 unless alpha plus beta is equal to 0, right? So in other words, whenever alpha plus beta is not equal to 0, this is 0. Right? So the only way, so suppose this was also 0, right? Then we will say that bf x alpha with anything, with any element of the Lie algebra, with any element of the Lie algebra equal to 0. Correct? That would be degenerate. So it's just a matter of non-degeneracy. So this was, I hope this is clear, right? Yeah. Right, because add the reason why this is, add x alpha will take, so it's purely off diagonal, right? Add x beta is also purely off diagonal, but in a different way, right? So when you take the product, that's always going to be 0 if alpha and beta, unless this happens to be. Or another way to say is that if I take, the way you prove that is the B of x alpha x beta is the same as trace add x alpha x beta, add x beta. right? And then we showed that this object is completely off diagonal. I mean, this, think of, before taking the trace, look at this matrix, right? So this add x beta, acting on x gamma, on x gamma, it takes you to x beta plus gamma, right? Now, so first I apply this. Now I apply add x alpha on that. So now I apply add x alpha on this. Then I'm going to get x alpha plus beta plus gamma, right? So unless alpha plus beta is 0, if alpha plus beta is not 0, you see the end result of these two operators is that x gamma is mapped to x alpha plus beta plus gamma. If alpha plus beta is not 0, then clearly it's completely off diagonal. This matrix is completely off diagonal, and therefore the trace will be 0. Right? So the only way it can be non-zero is if alpha plus beta is 0. Right? So that was the block structure. So the only way, I mean, so if I write the B matrix directly now, we can see that in this basis, if you have H, x alpha, x minus alpha, and so on and so forth, then if you look at now this block, this little block here, okay, this little block, I mean, this is the only possibility, right? Everything else is 0 here. I mean, sorry, if you look at this block, everything else is 0 here, right? So the only possibility, so the determinants, if I want to take the, if I want to take the trace, sorry, I'm talking about, so the only way that the determinant of B will be non-zero is if this determinant is not 0, right? So this is the structure of the B itself we're talking about, right? So B has, this is non-zero, here is non-zero, here similarly x beta, x minus beta, there will be another block here for the x minus x beta, right? Like this. So here is H, x alpha, x minus alpha here. Two of them. This is a 2 by 2 block here. X beta, x minus beta, then another 2 by 2 block, and so on and so forth. Huh? Then what we are saying is that this is completely block diagonal. Everything else is 0. Right? So when I take the determinant, it should be determinant of this times determinant of that times determinant of that, etc. So each determinant must be non-zero here. Right? But now if I look at this here, this little matrix, 2 by 2 matrix, is purely off diagonal form. Here it is 0, and here it is something. Here it is something. Okay. So the only way it can be non-zero, if the determinant can be non-zero, is if this thing is non-zero. Of course, yeah. Right. I mean, this also combining the fact that there is only the dimension of each of the space is 1, right? Dimension of each G alpha is 1 for alpha not equal to 0. So therefore, in each of these spaces, there is only one independent, linearly independent vector. Right? So I just call them as x alpha and x minus alpha. I mean, of course, it does not, I mean, we have this proof that this dimension of G is, alpha is 1, but even if it was not 1, suppose it was not 1, you just look at the non-linear, suppose this was, there were two linearly independent vectors with the same root alpha, okay? But then this argument that determinant of B is not equal to 0 would imply there should be also two linearly independent vectors here at x minus alpha, right? So that this will become 4 by 4 block. I mean, if it was a 3 by 2 block, you cannot have it, you know. So I mean, you cannot have just two of them and only one of them. It should be the equal number so that there is a pairing, and you know. But fortunately for our case, anyway, all the dimensions are 1, so there is only one linearly independent. Right. Anything else? Is that point clear? Yeah, that was crucial. That had to be non-zero. Otherwise, you wouldn't even get an SU2 structure right? I mean, if this happened to be 0, then you wouldn't have an SU2 algebra, right? And this whole thing is based on really the SU2 subalgebras. Anything else on this? I mean, until now? Because there are so many theorems we have gone through that so anything else here? Okay, then let me go back to the okay. So we went through up to this point. Which point? We have gone through the. We went through the table, right, in chapter 14. Chapter 14. So we went through that table. So the argument was, so we defined n alpha beta, which was the, where we are considering alpha string through beta. So this string is beta plus n alpha, where n starts from minus p to some q. Huh? This was, and we just n alpha beta was defined as 2 alpha beta divided by alpha alpha, and this was equal to p minus q. Right? That was one of the things that we obtained before. Okay. And beta alpha would be the same. Now it will be the beta string. So this will be alpha plus, say, n beta, where n will go from some minus p prime to q prime. These integers will be in general not the same. They'll be different. So n beta alpha will be the same, just expression 2 alpha beta divided by beta beta, which is equal to p prime minus q prime. And now the important point, this was that if I take the product of this n alpha beta with n beta alpha, that was simply if I take the product of these two, you get 4 alpha beta square divided by alpha alpha beta beta, which was the same as 4 cos square theta alpha beta. Right? And just summarizing what we did last time. And that's a very powerful statement, right? Because it's left-hand side is integers, so this also is integer. So first of all, we see cos theta alpha beta cannot be just arbitrary, right? There are not too many possibilities. It was just 60 degrees, 120 degrees, 45, 135, 90, and 30, 150. That's all. That's the only possibility, right? And we've also found that this restriction, because right-hand side is going to be less than or equal to 4, right? So this tells us that also these numbers cannot be too much, right? And those were the only possibilities which are given in the table. So, I mean, this number can be only 0, 1, 2, 3, 4, this product. But then we also checked, we showed that for 4, because if this is 4, then cos theta is either 0 or pi, so they are actually parallel, right? And we already know that, so in that case, beta must be equal to plus or minus alpha. There's no other choice, right? So for for this case, the only thing is beta equal to plus or minus alpha. Because we have already shown that, I mean, we see that beta and alpha are parallel, right? But we've also already shown that if alpha is a root, then if alpha belongs to delta, then C alpha belongs to delta only for C equal to plus minus 1, right? So, I mean, if beta is parallel to alpha, beta is going to be something, some number times alpha, right? But that number has to be plus or minus 1. So therefore, it's not different, and so we don't learn anything from that. I mean, we are interested in when alpha and beta are linearly independent. I mean, that is where one gets information about the details of the Lie algebra. So this we ignore, and 0 is an orthogonal case, and we can't learn much from this discussion at this stage. So the important points are these 3 cases, and in those 3 cases, we found that, I mean, this was one equation. The other equation, I can take the ratio n alpha beta over n beta alpha, which was now, this will cancel, and you just get beta beta over alpha alpha. So it also gives you the choice of these numbers gives you the ratio of the length squares. So it has a lot of information, these numbers. And then we had this table, which was, I mean, so the product of 2 integers is 1, 2, or 3. Certainly one of these integers has to be 1, plus or minus 1, right? So let's, without losing generality, let's choose n alpha beta and n beta alpha. Let us choose this to be plus or minus 1. It doesn't matter, because if it is other way, just rename alpha and beta. That's not the important part. So one possibility, so let's take the product equal to 1. Then if I choose this to be 1, that's also 1. Right? If I choose this to be minus 1, that's also minus 1. This is the case for this number equal to 1. Then we have possibility 2. In that case, again, 2, 1, minus 2, minus 1, and finally 3. So you have 3, 1, and minus 3, minus 1. These are the possibilities. And then we saw from this relation, since alpha beta, I mean beta alpha is always plus or minus 1, alpha beta is 1, plus or minus 1, 2, or 3. So clearly beta square, so beta square here, for this case beta square equal to alpha square. For this case beta square equal to 2 alpha square, and here for this case, and here beta square 3 alpha square. And angles were given also. Theta alpha beta, for this cases it was 5 by 120 degrees, or 60 degrees or 120 degrees. So maybe I should write here first. So theta alpha beta. So this is 60 degrees, this is 120 degrees, this is what, 45 degrees, 135 degrees. We're just computing the cos square theta alpha. So this number divided by 4. Right? And here it is 30 and 150 degrees. So this is it. Okay. And of course it also gives you the information of this, I mean these numbers of course have this information about P minus Q and P prime minus Q prime. So this is very, very restrictive, you can see. Because now you see, if for example in some of these, let's say in some case P minus Q, not at least one of them is not 0, right? Then what will happen? We'll have beta plus some number times alpha will also be there, right? Will also be a root, no? But then call that as some beta prime. Okay. Then beta prime and alpha must also have one of these angles. Cannot be something different, you see. So it's quite restrictive, right? I mean, it's not just the starting 2 vectors, no? Then you look at the chain. Each element of the chain must satisfy the same conditions. No, it should fall into one of these categories. No? or it could have or it could be perpendicular also, orthogonal also. But it has to be, it's very restrictive. Okay, to go a bit further, we need to, like what we did for SU3, we need to introduce a notion of positive roots, negative roots, and simple roots. So that is the next point. So the next point I want to discuss. So okay, in fact, one more thing that we went through last time was this proposition 14.1, which showed that you can have, at most spin 3/2 representation, right? The P plus Q is the total number of steps, right? Here, the P plus Q was between 0 and 3. That was it's a strong bound here. So any chain cannot be more than of this length. No? P plus Q is there. So it's because see the number of steps here. I think if I take beta here, beta is 1 point. Let's say beta is this one here, and I'm just looking at alpha and beta, so I can think of a plane. Because whatever is happening, all these vector sums are going to be still in that plane. It will not take you out of the plane, right? So it's enough to look at that. So beta plus alpha will be somewhere here. So this is beta plus alpha, beta plus 2 alpha, etc. And here will be beta minus alpha. So I'm just adding these two vectors, right, in the dual vector space. So the statement is that this chain cannot be more than these steps. No? So 3 steps, which means the maximum you can have 4 points in a string. Which means from the SU2, this SU2, which is X alpha, X minus alpha, and H alpha, this SU2 will act on this beta. It will be a spin 3/2 representation with respect to this SU2. Spin 3/2 is four states. So maximum it can be that. That's what it is saying. Okay, so the next topic is we want to introduce a notion of positive. Can I use this here? Concept of positive root. So for this purpose, what we do is again, you remember we made a definition of a regular element to define this Cartan subalgebra. We defined. Okay, here now I'm going to say it in a different way, but it's not very different actually. So the one definition is that H0 is said to be called regular element of Cartan algebra. Some array is there are infinite number of regular elements, but okay. So of the H, the Cartan subalgebra, if alpha of H0 is not equal to 0 for all alpha belonging to delta. All alpha belongs to delta. So you remember from the SU3, just to give you an idea, that this is not an empty set. You remember that, if I don't have that, do any of you remember that? We had this for SU3, just taking the example of SU3. We had alpha 1, if you write H is equal to AH1 plus BH2, where H1 and H2 were those bases, right? We chose H1 equal to 1 minus 1, 0, H2 equal to 0, 1 minus 1, right? That was it. So, and any Cartan subalgebra element I can write as a combination of H1 and H2. And then we wrote down alpha of H, I think it was 2A minus B. Alpha 2 of H was minus A plus 2B. and alpha 3 of H was A plus B, right? Now, you see, for generic values of A and B, I mean, obviously none of these three will be 0, right? For some special values, perhaps one of them might be 0. These are only non-zero, and the negatives are there. These are the only 6 non-zero roots, right? Each one of them, and then negatives, right? But you see that it should be very, very special situation where any one of them is 0, right? For example, if I choose B equal to minus A, this would be 0. Or B equal to 2A, that will be 0. But generically, I mean, in this two-dimensional space of A and B, those are some very special lines. So if I just draw A and B here, you see B equal to minus A is just one line here, right? Or you take B equal to 2A, B equal to 2A will be some line here, right? Or A equal to 2B will be some line here. So only along these lines, one of the alphas is 0, right? But generically, I mean, there are infinite number of points in this plane, right? Generically, if I take this point here, none of these roots are 0, right? So this is a generic situation. Actually, most of the elements are regular, in fact. I mean, the infinite number of elements are regular. The elements which are not regular are very small, measure 0 set. Because here you see just line. In a two-dimensional plane, one line is a measure 0 set. So this is a very generic situation. Because you remember, we discussed that the regular element is the one which has a minimum 0 eigenvalues, right? So if there is some H0 for which one of the alphas happens to be 0, then you see the number of 0 eigenstates is more. Because, of course, this commutes with all the kata. So that part is already there. But now you see that some non-zero root also gives you 0 eigenvalue for that. No? So therefore, that will not be a regular element. Yeah. And we are guaranteed that such element exists. As I said, generically, the elements are all regular. Generically. Okay, so given this, so let's choose one. Let's pick one regular element. Okay, and then define and then we can define the notion of positive and negative roots. So we take this H0. And we compute, so we can define an ordering. Once this H0 is there, I can define an ordering. Define an ordering between roots. So we say alpha and beta belong to delta. We say that alpha is greater than beta if alpha of H0 is greater than beta of H0.
Will that be true for every regular element?
No, it will be, of course, depending on which regular element you choose, ordering will be different. Right? But you can choose any one of them. The final result will be all equivalent. But this is just a step. I'll just come back to that.
That is manifestation of the fact that when you were teaching SUC, you said that you can choose any of the
precisely.
Positive and negative.
Yeah, exactly. Yeah. So in this picture, you see here, what we had is so we had this root was alpha 1 here, alpha 2 there, and alpha 3 here. Right? So if you exclude this line, we don't want a regular. We want a regular element, right? So if I chose some element which is like this, which some A and B's, which defines a line which is not passing through any of the roots. Okay, so call this as that H naught. Okay. Because H naught, it will be what this line says is the ratio gets fixed, right? Ratio between A and B get fixed, right? But then you can multiply by any number; it doesn't matter. So that's what I mean by this line. So the ratio is fixed. But ratio is fixed in such a way that this line passes below alpha 1, alpha 2, and alpha 3. No? Alpha 1, alpha 2, alpha 3 are on one side. Okay. Then if you define that thing, then you see that this will be, that ordering, this will be greater than that, and so on. Right? But more importantly, actually this notion is not so important, useful. I mean, what is greater? What will be is that what we will define is a set of positive roots, delta plus, is the set of roots belonging to delta such that alpha of H naught is positive, strictly greater than 0. And of course, delta minus will be the opposite, alpha H naught, strictly less than 0. You see, there is no 0. That was the reason for, because we have already chosen a regular point. So there is no 0 anyway. So it clearly splits into two parts. And so therefore we see that delta is equal to delta plus union delta minus, and delta plus intersection delta minus is 0. Whereas if you had chosen a regular element, you see that some alpha will be 0, so you cannot put in either of this set. No? So this is the reason for the choice of a regular element. Yeah, so here, if I had chosen this line to define that H naught, then from this point of view, alpha 1, alpha 2, alpha 3 will be positive roots. On the other hand, suppose I had chosen something else. Maybe I had chosen some line like that. Something like this. Then what will have? Alpha 1, alpha 3 and minus alpha 2 will be on one side. No? So those will be, one side will be positive and the other side will be negative. No? So but they're equivalent. They're not that they're going to give you different results. Final results will be the same. That's a matter of choice. Yeah. Okay. Now we come to the concept of simple roots. This part. Okay. So of course, this is just to kind of give some convention where you say, as we know that for every alpha there is an SU2 algebra, subalgebra, right? This positive and negative is just kind of giving you a definition of, what you call raising operator and lowering operator. X alpha if alpha is positive, it's a kind of, you think of it as a raising operator, and X of minus alpha is lowering operator.
X alpha is not equal to 0. Which roots are lying? Are they cut down?
So when we say, usually when we write delta is all the non-zero roots.
Okay.
Yeah, normally that's what we mean by that. So yeah, so yeah, exactly. So it's not karma. So in other words, all the non-zero roots, they are clearly split between positive and negative. Yeah, that was a good point. I should have mentioned that these really non-zero roots. So it's not in the karta part, non-zero roots. Good. So now we come to the important notion of simple roots. Okay. So simple roots. The definition is very simple. Actually, simple roots have a very simple definition. Now, you say, so some alpha belonging to delta plus, such that alpha cannot be written as sum of two positive roots. is called a simple root. What it means, so I'm taking some alpha belong to delta plus. If it can be written as some beta plus gamma, where beta and gamma both belong to delta plus, then this alpha is not a simple root. Okay? So the simple root, so then alpha is not. Then alpha is not a simple root.
So it's like choosing a basis?
Huh?
It's like choosing a basis for the root space?
Choosing a base, yeah, exactly. Yeah. That is what, I mean, that's what it will turn out to be, right? Okay. Right. So in some sense, you see, again, in that picture that we had, I unnecessarily erased it. In that picture of SU3, so we had this alpha 1, alpha 2, and alpha 3. And let's suppose I have chosen this some H0 along this line. Then these are the positive roots. Right? Now, somehow we want to find those roots which have the kind of minimum values of, when you evaluate alpha 1, I mean alpha 3, you see alpha 3 of H0 is alpha 1 of H0 plus alpha 2 of H0.
In the diagram, alpha 2 and alpha 3 are switched.
Right. Alpha 2, alpha 3, correct. Right. So this is just for the linearity, alpha 1 plus alpha 2. But each of them, what we are saying is positive, right? So alpha 3 of H0 is bigger than alpha 1 of H0 and alpha 2 of H0, right? So somehow we want to pick out from this. So anytime I can write like this, alpha equal to beta plus gamma, clearly alpha evaluated at H0 will be greater than their values for beta and gamma. No? So we are trying to find those roots, roughly speaking, which are closest to this line. Because the farther you go up, this will have higher value than these two. No? So we want to find the kind of smallest possible values. So this is the roughly the idea. And then we define, we give a notation, the sigma, I think what is it? Sigma, right? Yeah. We will define by sigma the set of simple roots. The set of simple roots. I mean, there will be more than one. Right? Like in SU2 case, we had two simple roots. So, but whatever the set of simple. So the important point is that these are those positive roots which cannot be written as sum of two positive roots. So if this is the case, then what we are saying is that alpha does not belong to sigma. Okay.
We can also write that beta equal to alpha minus gamma. Then we can exclude beta. I mean, why?
Beta equal to alpha minus gamma. No, but the statement is these are all in the delta plus. I mean, they are all in delta plus. I mean, if I write beta equal to alpha minus gamma, then you see minus gamma is in delta minus. No? So yeah, this statement is now all with the delta plus. Everything is here is delta plus. Okay, so now there are this definition looks so kind of broad. You know, I mean that it's hard to imagine that this definition will give you enormous information. You know, but it does. So there are several statements here. So we have so we'll call these simple roots. Simple roots. Let's give it some labeling. So sigma. So I will write it as alpha I. So alpha 1, alpha 2, alpha 3. So I'll just put some index alpha I. We don't know how many of them are there, but whatever the number of them, these are what I will call. So alpha I belong to delta plus, such that alpha I is not equal to some beta plus gamma, where beta belongs to delta plus and gamma belongs to delta plus. You cannot express that. That is the set. So first statement, this is theorem 14.1, that if alpha I and alpha j belong to sigma, then alpha I minus alpha j does not belong to root. All the roots, not just the positive or negative, I mean all the roots. So this is simply not a root. That's the first statement. The second is that if again alpha I, alpha j belong to sigma, then the alpha I, alpha j is less than or equal to 0 for I not equal to j. Because if I is equal to j, of course then it's alpha I, alpha I, that's a norm. That is, of course, we know is positive. But any two different ones, the dot product is negative. Which basically means that if you think in terms of these vectors, they have obtuse angle. No, because it will be the norms of the 2 times cosine theta. No? The fact that it's a negative or 0 or negative. 0 means orthogonal, but negative would means obtuse angle, greater than 90 degrees. No? Which was the case here, right? I mean, here alpha 1 and alpha 2 were the simple roots, and this angle was 120 degrees. So this was negative. Then the third important point is that so this elements alpha I, these elements of sigma are linearly independent. This is independent. And finally, the fourth point is that if alpha belongs to delta plus, positive root, then alpha can be written as sum over simple roots. Sum over, let's say, ni alpha I. Positive roots, these are simple roots, and these are, ni are non-negative integers, greater than or equal to 0 integers. So any root, in any positive root can be written as, where the coefficients are all non-negative. There is no negative term here. Of course, the negative roots will be just a minus of alpha. So this is for positive root. The negative root, it would imply that negative root will be again written as a combination of ni alpha I, but ni will all be non-positive. Okay? Because it's just multiply by minus, that's all. No? So in particular, of course, this implies that all the roots can be expressed as linear combination of simple roots. No? So it spans, of course, the root space. Okay, so the proofs are actually pretty simple. Okay, so this you prove by contradiction. Okay, so assume that it is it's a root. So let's suppose alpha I. So assume that alpha I minus alpha j is a root, right? It belongs to it.
So, what is the alpha i's in the fourth point?
Sorry?
Simple roots.
Here.
Yes, alpha i's are simple
Oh, the
roots.
simple roots, yeah. So I'm giving so this I goes from 1 to some number, whatever, m, let's say.
Okay. But the other alpha is not a simple root.
Other alpha is any element of delta plus. Yeah. At the end, it will become R, no? Because at the end of the day, we see that since everything is expressed in terms of combination of alpha I, and we know that alpha spans the full space, no? So therefore, alpha I themselves span the full space. But the full dimension of the Cartan subspace is R, the rank. So there will be R of them. Okay. So how do we? So we assume that this is assume that it is contrary to that. Then of course, if it belongs to delta, then either it belongs to delta plus or delta minus, right? So either alpha I minus alpha j is an element of delta plus or it's an element of delta minus. Okay. Now take the two cases. So suppose alpha I minus alpha j is equal to some beta which is in delta plus. Okay. I mean, there's some root. I can give it a name, beta. So there are two cases. Either so first case, let's say, and second case. So this is the first case. Well, if so, then alpha I equal to alpha j plus beta, right? And that's a contradiction because then we are saying that this is a simple root, whereas here is the sum of two positive roots, and that was against the definition. So this is not possible. And now, if second case, if beta is the negative root, which means I put here minus beta, alpha I minus alpha j equal to minus beta, where beta is a positive root. No? Any negative root can be written as minus or a positive root, right? This time you again do the other way. You take this on the other side, alpha j on this side. So you get here alpha I plus beta equal to alpha j. Again, a contradiction. So now this is another important, right? Because what it is saying is that if I look at the chain, say alpha I chain passing through alpha j, or alpha j chain passing through alpha I. Okay, P for both of them will be 0. You remember the P and Q. P will be 0 both of them. So it's like saying that the simple roots are like the lowest weight state. Lowest weight state of the other SU2s. So this is what was happening again to picture alpha 1, alpha 2. You see that from this SU2, which was the SU2 corresponding to alpha 1, here you had a doublet, which was alpha 3, right? But this was alpha 2 plus alpha 1. That was alpha 3. You don't have alpha 2 minus alpha 1. No? So from this SU2 point of view, when I think of this as a raising operator, right, then you see this only is raised, it's never lowered. No? So it's like the lowest weight state. And vice versa, if you look at alpha 2 chain with respect to alpha 1, alpha 2 string through alpha 1, then it is this doublet. Right? But again, it is raising, you see, going from there, not lowering. Lowering would have been gone down. So that is the statement. So this implies that there are lowest weight states with respect to other SU2. Okay. The second point. Yeah. So the second point is simply that if I look at the second point, if I look at alpha I string through alpha j through alpha j, j not equal to I, of course. This whole discussion is when j is not equal to I. I mean, if I was equal to j, then this would be 0. That will be in the kata. So we don't get when two different ones, alpha I not equal to alpha j. So in this case, if I look at this here, then remember this formula, which was 2 alpha I alpha j divided by alpha I was equal to P minus Q, where what is P and Q? It was a string alpha j plus n alpha I, n going from minus P to Q. Right? But we are saying that P is 0 because alpha j minus alpha I is not a root. Does not belong to the root. Right? So P has to be 0. Right? So that means it's a negative number. It's a 0. I mean, Q could be also 0, of course, in some cases, right? But whatever it is, it's not going to be positive. Since P is 0, that implies that alpha I alpha j is less than or equal to 0, because this is a negative. I mean, not positive. Could be 0 or negative. So it's always obtuse.
Second part is proved, right?
Yeah, sorry.
Second part is proved just as a philosophy of it.
Yeah, yeah, is a agreed, yeah. Okay, so now let's look at the third part. So let's assume the contrary again. That actually they are linearly independent, they are not linearly independent. Right? Then we'll come to some contradiction. That's the idea. So let's suppose so third point. Suppose they are not. Suppose they are not linearly independent. Okay. Then that means there should be some relation xi. I think here we are using. Okay, it doesn't matter. Xi alpha I equal to 0. I going from 1 to whatever the number is. Okay, let me just call it k. Yeah? Because at the moment we don't know whether it's spanning the whole, but so some k, whatever the number of elements is. So this must be 0. For some xi not equal to 0 at least. Huh? Because if all the xi's are 0, this is a triviality. That doesn't show anything. So this should allow, if I look at this equation, this should allow solutions where some non-trivial solutions for xi's, where not all the xi's are 0. Okay, so at the moment we don't know. Some of the coefficient will be positive, some will be negative. No, in the xi's could be positive or negative or 0. Okay, so what I do is I rewrite this equation into part. So the positive coefficients I keep it here, and the negative coefficients I take it on the other side. Okay. So now how to write it? Let's split this. So I will write it as let's write it as pi alpha I. So these are all positive. So I'm just looking at the positive parts. Whenever xi's are positive, I keep them on the left hand side, and I just call them pi. Yeah? And for the negative guys, so let me see what. So some of the xi's will be positive. So I will call them as pi. Some others, not the same index I, some other index I, say xj, is negative. Then I call them minus qj. Okay. So qj is again positive. Okay. And now I take all of these guys, all these coefficients which are coming with a minus qj, I put them on the other side. So that this equation is the same as equation, say qj alpha j. Okay. But remember that this, if I equal to 1 appears here, it will not appear there. No, these indices are different indices. So because I just separated the positive coefficients with the negative coefficients to put them. Okay. So this is the equation. So now here all the pi and qi, pi and qj are positive. Okay. If some coefficient is 0, it simply doesn't enter. So now I've just taken out zero coefficient, just remove it. Then what is left over is non-zero coefficients. Okay. Some of them are positive, some of them are negative. So I just separate them. So now let's take the square of this. The norm of this root, this combination, which is pi alpha I, is a combination of roots with the. So let's compute this. Just then by linearity of this, this is the same as pi p-l, let's say, alpha I, alpha l, where this I and L run over the range where this runs over. These are two different ranges. I don't know, let's call it. So this I belongs to, it's a range 1. And this is j belongs to range 2. These are two exclusive ranges, and there is no overlap between them. Range 2. So this both I and L are in the range 1. Okay. Now, on the other hand, if this equation is true, if this equation is satisfied, then I can replace one of these guys by that combination, right? So this quantity is the same as sum over pi alpha I, and with the sum over qj alpha j. So this is in range 1, and that is in range 2. So this is the same as that. And now I can write this as sum over pi qj and alpha I alpha j, right? So I in range 1, I will just write as R range 1, and j is in range 2. But here, since I and j, there's no overlap, these are all different simple roots, right? And we have already shown that these are all less than or equal to 0. So we are saying that this is less than or equal to 0. On the other hand, this is positive. I mean, this is we have already seen this positive definite. Once we are restricted to HR and the corresponding dual, that's all positive definite. Now we are working with the positive definite subspaces. Okay. So that's not possible, right? Because these are all non-negative integers. Okay. So the conclusion from here would be that all the so basically it just proves that all the pi equal to 0 and qj equal to 0. That's what. I mean, you see that here, the fact that this is 0, this is the norm of a vector, right? This is 0 implies. What I'm saying is that this is positive, right? This is strictly positive, or equal to 0. Strictly positive or equal to 0. So this is the norm, right? On the left hand side is we are sure it is less than or equal to 0. So it cannot be positive, but it can be 0. But if it is 0, since it is a positive definite term, I have all the pi's are equal to 0. And similarly, you go other way around, you can show all the q's are 0. Okay. So that shows that there is no such equation. If you write such an equation, all the xi's must be 0. That's what. So they are linearly independent. That's it. Yeah. Okay. And finally now, to prove this statement, that is again to prove this. So to prove this, the idea is simple. I mean, any root alpha which is not a simple root, any root alpha which is not a simple root, by definition, any alpha belonging to delta plus, and it's not a simple root, and alpha is not a simple root, then by definition I can write alpha is equal to some beta plus gamma, right? So beta and gamma are again in delta plus. Now two possibilities. Maybe both of them are simple roots. Then we have already shown, right? I mean, what we want to show is that every alpha belonging to delta plus can be written as combinations of simple roots. There are two possibilities. Either they are both simple, in which case we have proven, or perhaps one of them is simple. Then so suppose this happens to be simple, right? Then I can again go here, and since it's not simple, I can again write it as a sum of two positive roots, right? So you keep going, keep going. Eventually, since we are talking about a finite dimensional Lie algebra, it will exhaust, right? And at some point, you will end up with writing everything in terms of simple roots. Okay. That is it. This looks like a bit cheating, right? So you keep going. I mean, you see, at each point, you can see that clearly alpha of h naught is greater than the sum beta of h. I mean, is equal to beta of h naught plus gamma of h naught. And these are all positive roots. So these are all greater than or equal to 0. So at every step, this value is going smaller and smaller. No? But we are talking about a finite dimensional system anyway. So there are only finite number of roots. At some point, you start, when you try to rewrite this as linear combinations of positive roots, those positive roots will become, again, simple roots. There's nothing more you can go. So the result is that everything can be expressed with this here. And of course, in this process, we are never introducing a negative integer, right? We are writing alpha is equal to beta plus gamma, then perhaps beta, I write it as some beta 1 plus beta 2, gamma as some gamma 1 plus gamma 2. At every step, there are no negative integers floating around. No? So that is why this statement that alpha, the positive roots can be written as that combination, where all the ni's are greater than or equal to 0. Okay, so it's now okay, so one thing was here. And you can define, make a definition. You can define, since these are all non-negative integers, you can define a level of alpha belongs to delta plus, as simply equal to the sum over ni. If I write alpha is in this sum, then I define the level of alpha as simply the sum over ni. This makes sense because none of them is negative. Right? None of these are negative numbers. So there's an order. We are basically giving an order. Okay. 11, some kind of an ordering.
What is the meaning of this level?
No, it is just useful practically. It's nothing important actually. Because what we will do, I mean, I think I should. So it's a practical, I mean, because what we will do now is that you can specify, so the simple roots is enough. I mean, you just want to, if somebody gives you all the information about the simple roots, then you can construct everything else by step by step. So that is when you actually construct all the other roots, then you go level by level. No? So it's a practical tool actually. Of course, since it's a finite dimensional, this will not go indefinitely. Right? At some point, it will be bounded by something. Okay, just to let us write down all possible. I think maybe I should do that now. Let us try to. Okay, this is now the completely general thing. So what is the information that we can give with alpha and alpha j? So we have this say this root. So of course this means that number k is in fact the same as rank, right? After all this, it becomes a rank. So if somebody gives you all this alpha I, alpha j, and the n alpha I, alpha j. So in particular, there's maybe I should define that. Cartan matrix. There is something called Cartan matrix, which is just which contains the information about all these simple roots. So that has all the information, relevant information to construct the full Lie algebra. And this is given by the following. It's so we define a matrix So it's a R by R matrix. R is a rank. R is a rank. Rank is equal to R. So let's say R. So this will be a Kappa matrix is denoted by A. Okay, I don't know if it's a universal notation, but okay, we use this in the notes A. So this is an R by R matrix, whose the ith row and jth column is given by 2 alpha I alpha j over alpha j alpha j. This is unfortunate because actually this is from our old notation n alpha beta. This is actually n alpha j alpha I. So it's a kind of a transpose of it. But this is not important. I mean, it has, remember we were defining this as the n alpha beta. We were defining as the alpha string through beta, right? And this was 2 alpha beta over alpha alpha. But here, so the first index is appearing in the denominator, right? Here the second index is appearing. So it's like a transpose of what we were writing before. This is standard notation for the Cartan. In all the textbooks they use this notation. There is nothing more than a notation. Okay, so this information, basically this information you have to specify. And that encodes, that once you give me this information, what is Aij? Of course should be the allowed values, right? We already know that this n alpha betas are, z can be 0, 1, 2, 3, etc. 4, 0, 1, 2. This dot product can be 0, 1, 2, 3, etc. Right? So that with those restrictions, if you give me some Aij, then that fixes the Lie algebra completely. You can construct everything else, all the other generators, and construct the full Lie algebra. Okay. So this, therefore, then the whole problem of classification of all possible Lie algebras reduces to a purely geometrical issue, essentially. What kind of numbers you can give, right? Whether those numbers that you give is it geometrically possible to do, purely Euclidean geometry, nothing more than that. Huh? In some cases, when it is possible, there exists a Lie algebra. When it is impossible, okay, that Lie algebra doesn't exist. When it's impossible to have all those constraints satisfied, no? You cannot just arbitrarily specify all the dot products. No? For example, let's suppose I choose, suppose rank is 3. Okay? And I have alpha 1, alpha 2, and alpha 3, let's say. Okay. And let's suppose I specify that A12 equal to minus 1, A21 equal to minus A12, A13, and A23. All of them are minus 1. Suppose. Then what does it mean? This is minus 1, remember it meant that's 120 degrees. Right? First of all, the length squares are equal, and angle between 1 and 2 was 120 degrees. Right? Similarly, between 1 and 3, again the same thing. So try to draw it. So the first line I choose some direction. So let's say this is alpha 1. Then alpha 2 should be 120 degrees from it. 120 degrees from it. Right? This is alpha 2. Alpha 3 is going to be 120 degrees with respect to both 1 and 2. Right? The only thing you can do is that. But this is this is supposed to be 3 linearly independent guys, right? They should span a 3-dimensional space. But the only way you can get this alpha 1, alpha 2, alpha 3 satisfying this condition is to draw all of them in one plane. So it's 2-dimensional. It's not possible. You see. So this is just an example of that. I mean, that you cannot just put arbitrary numbers. I mean, it should be possible in a purely from Euclidean geometry point of view, that you should be able to draw such vectors, which have these possible angles. So there are a few restrictions, and it is by looking at these restrictions, which is purely geometric in nature, that they were able to completely classify all the simple D algebras. No? That is the how. That was a classification theorem. Okay. So what we'll do now? How much time I have? 5 minutes. No.
This Cartan matrix is sometimes given as a product of a root and a co-root. The 2 times alpha divided by that norm is sometimes also called a co-root.
Co-root is that thing that we mentioned, the map from alpha to H alpha. Yeah, you can go back and forth between root. This is a name. So these are the root, and then we had this map, right? This is possible to define in a semi-simple case where the Cartan-Killing form is non-degenerate, right? So we define this equation by simply alpha H equal to B H alpha H for all H. So that defined a unique element, H alpha, and that is what is called co-root. So of course you can define all of these things in terms of the co-root also. Actually alpha I, alpha j, alpha beta was the same as, up to some overall numbers, was the same as B, H alpha, H beta, right? So you can, in fact this is defined through that actually, right? And also, by the way, I remember that at one point I mentioned that we had some convenient factors we put, right, depending on the group. No, there were some convenient factors we put, which did not depend on which alpha beta you're talking about. Overall, for a group, SUN, there was a 1/2n factor or something. But those are totally irrelevant because you see, this important quantity involves the ratios. This is what is important quantity. Okay, and that is independent of that. Those constants will disappear from that. These constants are like if I take the SU3, if I change the constant, what will happen is that angle will still be 120 degrees. It is just that you're changing the length. Overall scaling of this, that is all. It doesn't do anything more. Now, so I don't think I can start now. But tomorrow, what I will do is I will just try to draw all the rank 2 cases, all the possibilities. Just 1 second. Those possibilities where we had n alpha and beta alpha was equal to 1, 2, and 3, right? 0, 1, 2, 3. So all these 3 cases we'll consider, and each of these 3 cases we will find a Lie algebra, the corresponding Lie algebra. In fact, this way we'll find SU2 times SU2, or SU2 direct sum SU2. Because we are talking about a complex, it's more like SL2 plus SL2. You can find SL3 and SO5, SP2. SO5 happens to be the same as SP2, and something new, which is what is called G2. Something new, which is not a classical group. So this way of classifying, they were able to find some new algebras which were not which are not classical.
G2 values like you choose a specific Cartan matrix and you can get G2.
That will correspond to that number equal to 3. This number being equal to 3. So this number equal to 1, we already know, that's SU2. That gives you SU2. The SU3, which we already see for the rank 2 case. Rank 2 case, when this number was 1, which was alpha 1, alpha 2, 120 degrees, right? When this is -1, more precisely, because when you talk about simple root, this is negative anyway, right? Non-positive. So it's going to be always negative. So unless I equal to j, the diagonal element you see, all the diagonal elements are 2 here, right? For this matrix, because if I equal to j, this cancels with that. So Aij always has a form. Diagonal elements are all 2, and off diagonal elements are either 0 or some negative number. And negative number has to be either -1, -2, or -3. That was a restriction coming from that. No? So this is the structure we have. And so when you have just one minus 1, you get that. When you have minus 2, so when this quantity, so as we said, one of them I can always put minus 1, say Nij, then Nji can be either minus 1, minus 2, or minus 3. Right? We can always choose one of them. It's a product of the two has to be 1, 2, or 3, right? But we can always choose one of them to be minus 1 because these are all, I mean, dot products are all minus. No? So one of them to be minus, and then I can choose all these 3 possibilities. This one gives you SU3. This one gives you SO5, or equivalently SP2. And this one gives you the new guy, G2. So we will go through this construction. Because that will give you an idea how, but just by knowing the Cartan matrix, you can step by step construct the full D algebra. So you don't need to know even what is my original, matrix group or whatever. You can just construct everything.
Sir, if there are number of simple roots, then the rank will be R cross R.
Rank will be R. I mean, rank of the D algebra is R, but this Cartan matrix is R by R matrix. What you say when you say rank is just a dimension of the semi-simple of the Cartan subalgebra, right? Okay, rank is just that's a definition. Right? And what we are saying is that since it spans the dual space, dual to the Cartan subspace, so since Cartan subspace the dimension is rank, this must also be R dimensional. And since it spans, it provides a basis. Okay, therefore there are exactly R such elements. Now this is a Cartan matrix. This is a Cartan matrix which is defined like this. So you see each of this I and j run over 1 from 1 to R. No? So that's why this gives you a R by R matrix.
What do you mean by classical group? Classical algebra.
Which one?
What do you mean by classical?
Okay, classical in the sense that, I mean, these are the matrix groups which we already knew from for various reasons, as some symmetries of physical systems. So it was kind of known in some sense. Even before all this classification happened, they were already known.
Like SOs and FUs, like SDLs and SPs.
Yeah, that was already known. SO we knew already, I mean, in the classical systems, as rotation group, right? Rotation symmetry. Or SUN, okay, not so much in classical, but yeah, you can also do some because that's more with the complex systems, no? Systems which have complex, involve complex numbers. But okay, still, that's just a slight extension of the SO group, right? And SP group we knew already from the the canonical transformations in the phase space. So these groups were known. I mean, maybe that is I don't know historical origin why they were called classical, but I assume that that's the reason. Okay, so I will go through this rank 2 case tomorrow, and I mean the chapter. Did you maybe try to read this chapter, which I didn't get any time to cover. Chapter 13, classical D groups. So there's a discussion about getting all the non-zero roots, right, for SO, SU, and SP. For all these 3 cases, you get all the roots. And so please go through that. If you find difficulty with that, tomorrow maybe we can also discuss that. This shouldn't take too much time, getting all these 3 algebras. No? SU3 we already know, so that we don't have to spend time. SO5 and G2. Those things shouldn't take too much time, maybe half an hour maximum. So we'll have still time. So either we can discuss this, if you tonight you can just go through quickly to see if you find it understandable or not understandable. Otherwise, I was thinking of doing something else, which is this appears a lot in physics, is the spinors. No? In the RQM, you have already done the Dirac fermions, gamma matrices you have done, right? So in general, this is in 4 dimension, right? I think what AD has been teaching is all about 4 dimension. 3 plus 1 dimension gamma matrices. But many times, in various contexts, in the context of string theory, Caruso-Klein theory, people are also interested in higher dimensional. So in general, one can ask, if I have given some SON group, right? Signature is not so important. You could have SON, comma 1 or something, whatever. But some SON group, how I will go about constructing the gamma matrices for them? No? And can I find out, for example, what is the dimension of the spinor? Like Dirac fermion is 4 component, right? Similarly, for some n-dimensional space, can I find out what is the what kind of a spinor I should look? How many components it must have? No. So this question, basically, that's a particular representation of not the SO, but the double cover of SO group, which is what is called spin groups. So can one construct the representations? So if I have time, I was thinking of just going through that construction, explicit construction of the spinor representation, no, for arbitrary dimensions. But we'll see whatever is it's not included in the lecture notes, but that is just for you to know how to. So we will see how it goes tomorrow. So if you can go through chapter 13, at least start, because already in the starting point, if you see that some things are completely unclear, then okay, then I can go through that tomorrow. But if you think that even if you have not understood everything, that you will manage to understand, say by the weekend or so, if you spend more time, then I will not do it, and I will go to. Okay, so see you tomorrow.
Did you stop recording?
Thank you.